Hello student, hi, good evening. So today we are going to see how to do the small signal frequency analysis for common emitter amplifier. Okay, so we are going to do here frequency response of the common emitter amplifier. Okay, so for which we will do the DC analysis as well as AC analysis. Okay, so then after that we will find the voltage gain. So let's see how to do that with one problem. So let's say I have one problem. So this is what I have given, one common emitter transistor. So this is my common emitter transistor. This is my NPN transistor, and this is my supply voltage of 10 volt, and this is my emitter resistance, which is this is my 2 kilo ohm, and this is my collector resistance. Okay, and this is my emitter resistance of 4.3 kilo ohm. Okay, 4.3 kilo ohm of emitter resistance, and here is my base, and this is my biasing resistance. These are the biasing resistance, and it is connected with this supply, and this is my 100 kilo ohm. Both are 100 kilo ohm. This is also 100 kilo ohm, and this is my coupling capacitor, which is coupled. Okay, through this coupling I am connecting here what small signal source, that is what over perturbation. Okay, so as an input signal, small signal input. Yes, this is my small signal input. Okay, so this is my small signal input, and here is my bypass capacitance, and here is my output side coupling capacitance. This is my CC1. So let's see, this is my 10 microfarad, this also 10 microfarad, and this is my 5 microfarad, and here I am going to connect one load of 2 kilo ohm, and this is my output voltage. Okay, so this is my common emitter amplifier, and with beta current gain of common emitter amplifier, this is given as 100. Beta is given as 100. Okay, so now I have to what we have to calculate here. We have to calculate the input impedance, we have to calculate the input resistance, output resistance, and voltage gain. Output resistance, voltage gain, and current gain. Okay, current gain. So this I want to find here from this common emitter amplifier. Okay, so first of all, what we have to do here, first of all we will go for DC analysis, because before going AC analysis, small signal analysis, we need to do DC analysis. Why? Because we need the collector current, DC collector current. Okay, so through which we can find the transconductance parameter, which is very important. Okay, so that's why we are going for DC analysis. Okay, so let's go for DC analysis, and please note down this, and after that you will understand how to do the DC analysis. Okay, so this is 100 kilo ohm, this is 2 kilo ohm, and this is 4.3 kilo ohm, 5 microfarad. This is output load 2 kilo ohm. Okay, so let's go for DC analysis. If you see DC analysis, in DC analysis, what happened in DC analysis? DC means what? DC means what? Frequency is what? 0 hertz. Yes, if frequency is 0 hertz, then capacitive reactance is how much? How much is the impedance of capacitor? That is, X is equal to 1 by 2 pi f. Yes, so here f is what? 2 pi fc, where f is what? 0 into something is what? 0, which is what? Infinite. Means Xc is equal to what? Infinite impedance means ohm, which means what? Open circuited. Yes, which means open circuited. Means in DC analysis, all the coupling and bypass capacitance get open circuited. Okay, get open circuited in DC analysis, because the frequency is 0. So X is, this is what? Capacitive reactance, which is nothing but the impedance of a capacitor, which is coming infinite. Infinite means what? Infinite means open. So all the coupling and bypass capacitance will get open circuited. So we are left with what? This collector resistance, NPN transistor, emitter resistance. Okay, so this is my biasing resistance, this is ground, and this is my 10 volt supply, and this collector resistance is how much? 2 kilo ohm, and emitter resistance is 4.3 kilo ohm. 3 kilo ohm, and this is my 100 kilo ohm, 100 kilo ohm, and this is also my 100 kilo ohm. Yes. Now, and beta is given as what? 100. Beta is given 100. Now we are going what? We are going to do first what? First we are applying the Thevenin equivalent. We are going to apply the Thevenin equivalent where? At base terminal. At base terminal. First apply the Thevenin equivalent at base terminal. Thevenin equivalent. Thevenin equivalent at base terminal. At base terminal. Okay, we are going to apply the Thevenin equivalent at base terminal. So what is that? If we apply the Thevenin equivalent at base terminal, then what? Then Thevenin voltage will be equal to how much? VTH is equal to, apply the voltage division rule here across 100 kilo ohm. So 100k into supply voltage 10 divided by 100 plus 100. If you see, it will come 100 means it will come 5 volt. Yes, it will come 5 volt. Yes. So this is what? 5 volt. So VTH is what? Over VTH is nothing but 5 volt. 5 volt. And RTH is what? RTH here. RTH is nothing but over base resistance. Base resistance, which is nothing but 100k parallel 100k. 100k parallel 100k is equal to what? Is equal to 50k. 50 kilo ohm. Yes, 50 kilo ohm. This is my base resistance, means RTH 50 kilo ohm and VTH 5 volt. So now what we are going to do? So now we are going to draw the DC equivalent circuit for common emitter amplifier. So let's see DC equivalent circuit for common emitter amplifier. How to draw that? So let's see with the help of this Thevenin equivalent. Okay, so we will replace this by Thevenin equivalent, that is what? 5 volt and 50 kilo ohm. Okay, equivalent circuit for common emitter amplifier is obtained as, this is my conductor resistance, this is my NPN transistor, and this is my what? This is my emitter resistance, and this is my supply voltage of 10 volt, and this is my 2 kilo ohm resistance, and this is my 4.3 kilo ohm emitter resistance, and this is my base resistance of how much? 50 kilo ohm, and this is my Thevenin voltage that we have obtained. How much? Thevenin voltage. Okay, so positive, negative. How much is this? 5 volt. Yes. Now we have what? We have converted the bias resistance, bias side at the base terminal. We have applied the Thevenin equivalent. Okay, so this, now here we are going to, and beta is given as 100, and here we are going to calculate what? Collector current. This is our main motive of doing this DC analysis. For what? Collector current. We want collector current, DC collector current. First, for that what we will do? So let us apply the KVL in this loop 1. Yes, by applying KVL in loop 1, what we will get here? So this is my 5 volt, 5 minus IB RB minus, if you know very well, I think you might have seen that the cut-in voltage of this NPN transistor is how much? 0.7 volt. Means VB is what? 0.7 volt. Okay, so this is my minus 0.7 volt minus IE RE minus IE RE. Okay, so now IE RE is equal to what? 0. Is equal to 0. So here, now as we know from our base, as we know that emitter current is equal to what? Beta plus 1 into IB. Beta plus 1 into IB. Okay, so now here by putting this value here, what we will get? 5 minus 0.7 minus IB I am taking common. Now here RB, and in place of what? IE, so here IE is equal to IB into beta plus 1, so that is what? Plus beta plus 1 into RE. Okay, so RE. Now therefore base current is given as IB is equal to 5 minus 0.7 divided by RB is how much? 50 plus beta plus 1 means 101 into what is RE? RE is my 4.3. Yes, RE is how much? 4.3. Okay, so this is my milliampere. This is my milliampere. Now when we solve this, how much we will get here? 5 minus 0.7 is 4.3. Yes, 4.3. So if we calculate this here, IB is equal to 4.3 3 divided by, here is 50, 50 plus 101 into 4.3. If we will calculate that one, so what we will get here, if you see, this is nothing but 101 into 4.3, this is my plus 50, this I will get into 4.3, 8 point, okay, so this is my in milliampere, okay, so and here IB, that I will get here 0.008, 0.008878, 0.08878, 8 milliampere. So this is my IB, yes, base current, this is my base current. Then what will be the IC? IC will be equal to beta IB. So how much is this? Beta is nothing but 100 into IB is what? 0.008 when we multiply this with 100, so what we will get? 0.887. So IC will be equal to 0.887 milliampere of current. So this is what IC. We have got DC collector current as 0.887 milliampere. Okay, so DC collector current that we have obtained as 0.887 milliampere. Okay, 7 milliampere. This is my DC collector current. Now see, if you see how much is VC, VC is equal to 10 minus 2 into 0.887. Okay, so volt, because 2 is in kilo, so milli and kilo will get cancelled out, and VC is nothing but, this is how much? 2 into 0.887, so this will be into minus 1 plus 10. So this is my 8.226 volt. Yes, this is my collector voltage. And how much is my VA? Emitter terminal voltage is how much? That is VE is equal to IE into RE. So IE into RE. So how much is IE? If you see, IE is nothing but, this is beta plus 1 by beta into IC. So which is nothing but here 101 by 100 into 0.887 milliampere. Okay, 7 milliampere. How much emitter current will come? Emitter current is nothing but, if you see here, 101 divided by 100, so multiply this with 0.887, so we will get 0.895 milliampere. Yes, emitter current is how much? 0.895 milliampere. Okay, so IE is equal to 0.8, so this is my 0.895 milliampere, 5 milliampere. Okay, so when we will put this IE here, what we will get? VE. So emitter voltage, how much we will get? 0.895. So emitter voltage will be obtained as VE is equal to 4.3 into 0.895. Yes, 0.895. Okay, so volt. So how much is VE? VE is nothing but 4.3 into 0.895. So it will be 3.84. Yes, 4 volt. So this is what my VE, 3.84, 8.226. Yes. So therefore VC is how much? How much is VC? Why we are checking this? VC is how much? VC is equal to VC minus VE. VC minus VE. So which is equal to, VC is nothing but here, that we got 8.226 minus 3.84. Yes, 3.84. If you will do this, how much we will get? This will come 4.37. So therefore VCE is how much? 4.37 volt. So this VC is what? VCE is greater than 0.2 volt. Yes, 0.2 volt. 0.2 volt means what? 0.2 volt is the saturation. Okay, so VC set. saturation voltage of collector to emitter voltage, that is 0.2, but it is coming greater than 0.2 means it is, therefore our transistor is working in active mode. Okay, so it is operating in active mode. So that is why we want to check whether this transistor is operating in saturation active cutoff region. So therefore we have checked that our transistor is working in active region and hence it can work as an amplifier. Okay, so now we will jump for what AC analysis of the amplifier. Okay, so this is the condition that we should check. Okay, so we should check if we see it is less than VCC by 2 supply also. VC is what? VC is VCE, okay, collector to emitter voltage, which is less than supply voltage by 2, means if it is greater than supply voltage by 2 also, it will go in what? Unstable state. Okay, so there what thermally, so if VC is greater than 5 volt means it is not thermally stable, but it is coming less than 5 volt, so means supply voltage by 2, so it is thermally stable also, and it is also working in the active region. So that we can say that yes, the transistor is properly working in active region and hence it will work as an amplifier. So now see, we are going to find what? We are going to find the small signal parameter before going to the small signal analysis of this amplifier. So we have checked all the condition about this transistor, where it is operating. Okay, so and is it thermally stable? Yes, it is thermally stable. Why? Because the VC, collector to emitter voltage, is coming less than supply voltage by 2. Supply voltage by 2 is how much? 5 volts. So it is coming less than 5 volt, means it is stable. It is thermally stable as well as it is operating in active region. So let's see. Now we are going to find what? We are going to find the small signal parameter of the amplifier, so which is very important to draw the small signal equivalent circuit. Okay, so before going to the small signal analysis, we are going to find what? We are going to find the small signal parameter of the common emitter amplifier with the help of obtained collector current. So obtained collector current, how much that we have obtained? So that is 0.887 milliampere current. Okay, so what is main important small signal parameter of the common emitter amplifier? So that is first is transconductance of an amplifier, so which is represented by GM. So this GM is nothing but what? Transconductance. This is what? Transconductance. Okay, so this is transconductance of amplifier. This is very important parameter of amplifier, so which will drive what? Input. Okay, so input with amplification at the output side of the amplifier. Okay, so that is what? A very important parameter, transconductance of an amplifier. So transconductance of an amplifier is given as GM is equal to IC by what? IC by VT. What is VT? VT is nothing but it is a thermal voltage. What? Thermal voltage. So thermal voltage at room temperature is nothing but it is KT by Q. What? KT by Q? Yes. What is K? Is the Boltzmann constant and T is the temperature. Okay, and Q is the charge. So when we convert this KT by Q, so if we will write this KT by Q, so this is nothing but, if we see at room temperature 300 divided by 11,600 volt. Yes. So that is what, when we put the Boltzmann constant value and charge value, okay, so Q by K, so then it will come. So and we are going to convert this into electron volt. Yes. So this is what? Boltzmann constant. What? Boltzmann constant. So it will come like this. Okay, so this much value will come when we will calculate this both Boltzmann constant and charge value. So it will come how much? It will come 0.02586 volt. Yes. So therefore our VT will be equal to what? VT will be equal to 25.86 millivolt. What? Millivolt. So this is my what? This is my thermal voltage at room temperature. Okay, room temperature. So now therefore we get the transconductance as how much? This is collector current that we have obtained as 0.887 divided by thermal voltage is how much? That is 25.86 millivolt. So this is my ampere per volt. Yes. So milli will get cancelled on both sides and it become ampere per volt. So therefore my transconductance will become equal to how much? If we will divide this, how much we will get? 0.887 divided by 25.86. Okay, so this is nothing but, here it will come 34.3. So it will come 34.3 milliampere per volt. Yes. So this is my transconductance of the common emitter amplifier that we have obtained. How much? 34.3 milliampere per volt. Okay, so now we have obtained the transconductance, first small signal parameter, and second small signal parameter is what? Second small signal parameter, that is over AC resistance of the transistor. What is AC resistance of the transistor? Is nothing but this is my R pi. R pi is equal to what? Beta by Gm. Yes, beta by Gm. Beta by Gm. So this is my AC resistance of transistor. So that is nothing but 100 divided by Gm. That we have got how much? 34.3 kilo ohm. When we will divide this, how much we will get here? So this is nothing but 100 divided by 34.3. So it will come 2.915. So it will come approximately 3 kilo ohm. Yes, approximately it will come 3 kilo ohm. So therefore we have obtained the two small signal parameter of an amplifier, which is very important, that we have got here. R pi we got 3 kilo ohm, and Gm that we got 34.3 milliampere per volt. Now we are eligible to draw the small signal. Okay, so now we are going to do the small signal analysis of the common emitter amplifier. Okay, so now we are eligible to draw the small signal equivalent circuit of the common emitter amplifier. Now see here, small signal analysis or common emitter amplifier. Small signal analysis for the common emitter amplifier. Common emitter amplifier. Small signal analysis for the common emitter amplifier. Now we are going to do the small signal analysis for the common emitter amplifier. Yes. So in small signal analysis of the amplifier at mid frequency region, where at mid frequency region, where we are going to do the small signal analysis at mid frequency region. Okay, at mid frequency region. Okay, so at mid frequency region, what happened? At mid frequency region, if you see here, all the coupling and bypass capacitance get short circuited. Okay, short circuited. If you see at mid frequency means it is somewhat middle range of frequency, where over Xc will come very large. So Xc will approach to 0. Okay, Xc will approach to 0 because mid frequency region is somewhat in the range of kilohertz range. Okay, so mid frequency range in the range of megahertz. Okay, so mid frequency range, due to which this reactance component, this capacitive reactance impedance will get approaches to 0, means which implies that it get what? Short circuited. This will get short circuited. This means what? All the coupling and bypass capacitance will get short circuited at mid frequency region. Okay, so mid frequency region, and all the internal capacitance of the transistor will remains open circuited because it will come into the picture at very high frequency, but not in the mid frequency region. Okay, so that is why all the coupling and bypass capacitance will get short circuited. Now see the small signal analysis, how they will get short and which component will get eliminated, which element will get eliminated from this. See here, small signal analysis. In small signal AC analysis, I am writing just AC analysis. So what will happen here? So if you see this is my conductor resistance. Okay, so this is emitter resistance, and this is my what? This is my bias resistance. If you see here, now this supply voltage will get what? Grounded. This will get ground, and this also will get ground, and here this coupling capacitor will get short circuited, and this input signal will get connected. Yes, small signal get what? Coupled through this coupling capacitance. Yes, and here also this is my emitter resistance, which will get bypassed by this bypass capacitance. Yes, this bypass capacitance will also get short circuited. Yes, and here output capacitance also get short circuited, and here load will come into the picture. Okay, so this is what? V0, positive, negative. Yes, this is my AC analysis, small signal analysis of common emitter amplifier. Yes, these are my bias resistance. Yes, now we are going to draw the small signal equivalent circuit for this AC analysis. Okay, so let's see how to draw that. We are going to draw the small signal equivalent circuit. This is small signal analysis. Okay, so where all the capacitance get short circuited, bypass capacitance as well as coupling capacitance. Okay, so now and this emitter resistance will get bypassed by this bypass capacitance. Okay, so therefore the small signal equivalent circuit will be obtained as, let's say, small signal equivalent circuit. How to draw the small signal equivalent circuit? So this is what small signal equivalent circuit, small signal equivalent circuit. Okay, at what? At mid frequency region, at mid frequency region. Okay, mid frequency region. How to draw the small signal equivalent circuit at mid frequency region? That is what you see here. First, this is my input small signal input Vi, that we can call it as a perturbation, very small amount of signal in the range of millivolt. Yes, it will get coupled through this transistor amplifier, and here is my base resistance. Okay, so this is my base resistance, which is the parallel combination of bias resistance, and this is my AC resistance. What AC resistance? R pi of the transistor. Yes, here is my voltage V pi, positive, negative, and this is my current source. Yes, current source, with this current source is what? How much amount of current is there? This is GM V pi. Okay, so now here is my collector resistance, and assume that there is no base width modulation. Base width modulation is neglected here, means lambda is equal to what? 0 volt inverse. Yes, this is my 0 base width modulation, means output impedance will not come into the picture. It is very large, infinite. Okay, so which is already open circuited. Okay, so now see RC, then here is my parallel resistance RL, and here is my output V0, positive, negative, and this will get emitter resistance will get bypassed by bypass capacitance. Yes, short circuited bypass capacitance. Okay, so this is my base terminal, here is my collector terminal, here is my emitter terminal. Okay, so this is what small signal equivalent circuit for common emitter amplifier. So now we are going to find first input resistance seen from the input side, and output resistance seen from the output side. Yes, output side. How much is this? If you see, Rin is this, and R0 is RC, and Rin is what? Parallel combination of RB and R pi. Okay, so let's say I will calculate this here. Every calculation I will do here only, because I have to keep this circuit with me. So here is base, and here is collector, here is emitter. So our input is how much? Input resistance is what? RB parallel here, R pi, which is equal to, RB is how much? 50 kilo ohm, and R pi is how much? 3 kilo ohm, and which is equal to, if we solve this, we will get 50 plus 3. Okay, so reverse, into 50 into 3. So this is what? 2.83. So it will come 2.83 kilo ohm. This is my what? This is my input resistance, and what is my output resistance is similar to what? RC, which is my 2 kilo ohm. Yes, my input resistance for this common emitter amplifier, that is 2.83, which is parallel combination of this, and R0 is my RC, just RC, 2 kilo ohm. Yes, now here we are going to calculate what? We are going to calculate the voltage gain of an amplifier. Yes, input resistance that we have obtained, and output resistance also that we have obtained. Okay, now we are going to calculate the voltage gain of an amplifier, of a common emitter amplifier. So let's see here. Again, I am going to rub this, because this circuit I want to keep with me, so that I can see it properly. Okay, so let's see here. Voltage gain. For voltage gain, first of all, I am going to apply what? KVL. I am going to apply KVL in this outer loop 1. Okay, so here, so therefore the V0 is equal to how much? If you will apply the KVL, this current is what? This current is going like this, and it is coming from down to up, means positive to negative. Okay, so therefore if I will apply here KVL, what I will get? V0 plus, I will get V0 plus GM into RC parallel RL is equal to what? 0. So therefore what I will get here? V0 is equal to minus GM into RC parallel RL. Yes, here is also into what? V pi is also there. So into V pi yes, into V pi. Now this is, now I want to what find this value V pi, okay, in term of Vi. So what is this? Now by applying the KVL at the input side, when we apply the KVL at the input side in loop 2, what we will get here? Vi minus V pi is equal to what? 0. So if you see here, Vi is equal to V pi. Okay, so this is my V pi is equal to Vi. Now I will put this V pi into this output voltage, so therefore I will get the voltage gain as. So let's see, I'm going to again remove this. Okay, so therefore finally we get the output, we get the voltage gain as, if you see here, V0 is equal to minus Gm RC parallel RN into Vi. So therefore my voltage gain will be equal to AV is equal to what? V0 divided by Vi is equal to minus Gm into RC parallel RL. Yes, RC parallel RL. This is my voltage gain. What? Voltage gain. Now see here, RC parallel RL is how much? How much is RC? 2 kilo ohm. 2 kilo ohm. How much is RL? Also 2 kilo ohm. Both are 2 kilo ohm. So therefore RC parallel RL is nothing but how much? This is 2 kilo ohm. This also 2 kilo ohm. So this is nothing but 1 kilo ohm. Yes, this is nothing but how much? 1 kilo ohm. 1 kilo ohm. Now I know Gm, how much is that? 34.3 milliampere per volt. So therefore overall voltage gain is obtained as how much? Overall voltage gain is obtained as AV is equal to V0 by Vi, which is equal to minus 34.3 into 1. Okay, so 1 is in kilo ohm, 34.3 is in milliampere per volt. Yes, milli and kilo will get cancelled out and we are left with volt by volt. Yes, so therefore we got how much voltage gain? Minus 34.3 volt. 34.3. This is what voltage gain of an amplifier that we got. Yes, common emitter amplifier. So now see how to find the current gain. We have obtained the voltage gain. We have obtained the voltage gain. We have obtained the input impedance, and we have obtained what? We have obtained the output resistance, input resistance, output resistance, and voltage gain. And we are left with what? Current gain. What is current gain? If you see here, current gain is nothing but AI is equal to I naught by I. If you see here, output means output is coming from this side. Okay, so this means what? I naught is equal to what? I naught is equal to V0 by Vi, V0 by what? R naught, V0 by R naught divided by input current is how much? That is Vi by Ri, Vi by Ri. Yes, Ri. So which is nothing but, if you see V0 by Vi, if you see here, current is coming like this. Okay, so means it is coming from negative side, this side. So this is also what? Negative. Okay, so minus V0 by R naught current. It is coming from ground side. Okay, so that's why it is negative. And if you see voltage, V0 by Vi into, and this is what? My Ri will go upside and R naught will come down. So this is why what? R naught. So this means it is what? Voltage gain minus voltage gain into R input impedance or resistance, input resistance upon output resistance. This is my current gain. Okay, so I know all this value. So just put here what we will get. Finally, the current gain as. So finally we get the current gain as I naught is equal to voltage gain. So that is what? Voltage gain into what? Minus voltage gain into input resistance upon output resistance. How much is voltage gain? That is negative positive 34.3 into, this is Rin is how much? That we got here 2.8 kilo something here, 2.8 divided by R naught is what? 2. Yes, if you see, we got here 50 plus R pi is 3, reverse into 50 into 3. So this will get 2.83. So this is 2.83. So which is equal to divided by 2 into 34.3. So this is how much? 48.53. ampere by ampere. Yes, this is my current gain. How much current gain that we have obtained here? This is 48.53. Yes, 48.53. So finally we got the current gain as 48.53 ampere by ampere. Yes, ampere by ampere. We got voltage gain as minus 34.3 volt by volt. Yes, we got input resistance as 2.83 kilo ohm, and we got output resistance as 2 kilo ohm. Yes, this is what we got. We got voltage gain, current gain, input resistance, output resistance for the given common emitter amplifier. This is the way of how to calculate voltage gain, current gain, input resistance, output resistance, how to do the small signal analysis, how to do the DC analysis. Okay, so why DC analysis is important? Because our main motive is what? Transconductance. For transconductance, what we need the collector current. With the help of collector current, we are able to calculate the transconductance, because the transconductance is one of the most important small signal parameter which will help to boost this input perturbation, small amount of signal at the output side, which will amplify it with greatest amount. So this is the role of this transconductance parameter as in a small signal parameter of the common emitter amplifier. So I hope so you have understood it very well. Okay, so how to solve this type of problems related to common emitter amplifier. Okay, so how to do the DC analysis, AC analysis of the amplifier. So thank you very much.